So this says your turn, and it's true. I will make you draw some of these, but we can go over a couple of them together. We'll draw this first one and this last one for you. But really, you should pause and try to draw them on your own and then check how I have drawn them. So if we look back at our how do you know when to consider resonance, are we in 1, 2, 3, 4, or 5? Number 1, an atom with a positive charge and less than an octet. Atom with a positive charge and less than an octet next door to a pi bond. That's where we are. So my pi bond swings over next door. Remember, this is like my hinge carbon. Swings over next door to share electrons to make a new pi bond there. So if this carbon had a positive and we just gave it new electrons, it does not have a positive anymore. This one was my hinge carbon. It had four bonds in the beginning, 4 bonds now, no positive. This carbon is the positive that lost electrons, the carbon. This carbon is the atom that lost electrons. So it gets a positive charge. Stop and analyze again. An atom with a positive charge next to an atom with a positive charge and less than an octet next to a pi bond. Yep, we've got it again. Swing that partner, do-si-do, flip that pi bond next door again. Pi bond here, pi bond there. This carbon is the one that lost. That carbon is the one that's positively charged. Pause and analyze. An atom with a positive charge and less than an octet next door to a pi bond. Well, it is next door to a pi bond, but we just moved that one. Don't go backwards. Keep trudging forward. But an atom with a positive charge and less than an octet next to an atom with an unshared pair. Yep, that's what we have now. We have an atom with an unshared pair next door. So that unshared pair can become a shared pair of electrons to give me this. My handwriting is never terribly neat, but on this electronic thing, it's really kind of bad. I apologize. 2 pi bonds stay, and I have a new pi bond between oxygen and carbon over there. This carbon now has 4 bonds and a full octet, so no positive. But this oxygen is now sharing more than he'd like, and he tells us he's grumpy with a positive charge. So if I consider these 4 resonance contributors, who's the winner chicken dinner? Is there a winner chicken dinner? Is one or any more important than any other? Yes. This blue one is the most important resonance contributor. How do I know? The number 1 rule is octet. Does everybody have an octet here? Nope. Carbon without an octet, carbon without an octet, carbon without an octet. Ooh, carbon has an octet, and so does everybody else. So this is my winner chicken dinner. What does it mean to be winner chicken dinner? It means that blue molecule contributes more to the hybrid than any of the others. Yep. Before we move away to our next example, there's something that I want to point out, something that I maybe should have said prior to now. Carbon that has 3 bonds and a positive charge is called a carbocation. It's not really a functional group, but it's a reactive intermediate. And so when I ask you things, in the beginning, we sometimes do categorize that as a functional group, but really all I mean by that is it's a structure that I need you to recognize and know the name of. Carbon with 3 bonds and a positive charge is a carbocation. Carbocations have less than an octet and they want electrons. They love electrons. They need electrons. So anytime you see a carbocation, you're on a mission to try to find something that has electrons to share with a carbocation. Got it? Cool. On to our next example. While we're talking about carbocations, is this a carbocation? No. That's a carbon that has 3 bonds and a negative charge. A carbon that has 3 bonds and a negative charge has a lone pair. It's not a carbocation, it's a carbanion. It's also a reactive intermediate, not exactly a functional group. But we're going to kind of group it the same for right now, as in carbon with a minus is a carbanion. That's a structure I need you to recognize. A carbanion has a negative charge and a lone pair. So, carbanions, carbocations, 2 new things to add to your sort of functional group list. All right, to this example. We've said this carbon has a negative charge, so it has a lone pair as well. Situation number 1, nope, no positive charge. Situation number 2, atom with a negative charge next door to a, that's where we are. Lone pair gets donated toward the pi bond to make a new pi bond. That would explode this carbon's octet, so you gotta move it out of the way to the corner. Remember, we're moving as few electrons as possible, so we're moving that thing only to the corner. Done. Can I keep going? Yep. This lone pair can now go to make a new pi bond here, and this pi bond gets kicked to the corner. Pi bond got kicked to the corner, that's a new negative. Okay, can I keep going from here? This thing, donate here. No. Don't do it. This is an sp3 carbon. That cannot accept electrons. Do not try to give it any electrons. So we're finished. There are 3 resonance contributors of this thing. Is there a winner chicken dinner? Is anybody more important than anybody else? Nope. They are all equivalent. The hybrid is a pretty equal mixture of all 3 of those resonance contributors. That's kind of cool. Now it's really your turn to do the other 2 and be prepared to talk about them when we have our next class together.